All right, I'm happy to introduce Igor, who's going to tell us about using Ubuntu and MicroK8s on very serious computers.
Yeah, thank you so much, and welcome to my talk. As announced, I will talk a little bit about how we are using Ubuntu and micro-Kubernetes in research facilities like Center for Free Electron Lasers in Germany or San Diego Supercomputer Center in the United States. So, a little bit about me. I have a quite extensive software development background. It's more than 15 years. Within those 15 years, more than 10 years I spent in scientific software development, and within those 10 years, I spent 3 years being a kernel contributor to the open source SCADA framework. And SCADA stands for System Control and Data Acquisition. I will explain a little bit later on. And after those 3 years, I spent 1 year in a steering committee for that framework, deciding on some strategic decisions. And I also find myself being an event-driven system architect and a reactive programming advocate within the scientific development communities. And as photo suggests, I'm really keen to travel, and I try to travel a lot. And I talked a little bit to the people in the hallway and others community groups, and apparently when you start talk about big research facilities, everybody knows Large Hadron Collider, which is great, but I want to bring you the fact that there is a much more facilities than just Large Hadron Collider. So typically, those are huge territories with a lot of buildings. It's called campus, and every research facility has its own feature. This one specifically is located in Hamburg. It's called DESY, so Deutsches Elektron- und Synchrotron. It's basically a synchrotron facility. So we have this nice fancy ring highlighted in orange on the photo. And this one is underground, but if you look for other facilities in Europe, so for instance, Max4, UISRF, or Solaris, there's a bunch of them. I know at least a dozen of such facilities across Europe, and also in the United States. You will clearly see the rings there, so it's typically a round building. And in Hamburg, we have just a part of that building. It's highlighted in blue on the photography, and then on the schematics, we see a part of the ring again, and then this building from the inside. So we have a storage ring, so-called storage ring, where the particles are flying, and then they eventually enter so-called beam lines, and every beam line is ended with a so-called end station. And end station are marked in orange dots on the schematic presentation, and those dots, if you look inside, typically represented by a really diverse bunch of hardware. So it's called scientific instrument. This is where the actual science happens. So users come with the different samples, different ideas, prepare the send stations, and then shoot the targets with the particles. So, and also these facilities, I would say almost always features also high performance computing, because all the data gathered from the end stations then goes to the clusters and being processed. How this all happens? If we look inside the storage ring, again, it's this banded tunnel with tons of the hardware. So typically some beam position monitors, vacuum pumps, and different motors, so on and so forth. And the SCADA is a piece of software which glues this hardware on one picture with the people on another picture. So it provides a feedback, so how machine performs, or scientific instrument, and again, SCADA stands for System Control and Data Acquisition, so it basically controls the hardware, gets the feedback, acquires the data, and so on and so forth. And these pieces of software can be of different sizes. So the one I contributed in was huge. It's used almost at every research facility in Europe. But as a hobby project, I developed my own flow control system for this custom hardware. A friend of mine, a scientist, asked for such a solution because there were specific requirements. I will cover those requirements in a second. Here we see this hardware disassembled. So normally it's in a crate. So we have controllers, motors, router connected to the outside world, and a Raspberry Pi. It's all in a crate, and you can then move it from one beamline to another, and even across the world. So this one specifically traveled to Hamburg, to South Korea, and as I said, there is many different SCADA systems, and at every facility, usually, well, in Europe they tend to use the single one, but across the globe there are multiple SCADA systems, and so the main requirement for that control system was to be able seamlessly integrate it into the host SCADA system. So idea is that this scientist comes to facility, installs the hardware, and then we have as little as possible downtime due to integrating it with a host SCADA system. And so how we achieved that? On a Raspberry Pi, I had a Ubuntu server running a micro-Kubernetes, and then there is a bunch of software components running on that micro-Kubernetes, which are responsible to solving that solution. So, as I said, it's deployed on micro-Kubernetes. Here we just see some pods running in micro-Kubernetes, and I also put some GUIs screenshots. It also provides a headless API, but yeah, I couldn't find a good way to demonstrate a headless API on the slide. So, summarizing this first case, I find it is very nice that we have this micro-Kubernetes, because now I use it as a showcase, not only for this specific solution, sorry, but also demonstrating scientific software developers, like, let's say, best practices of software development in the companies. Because having this micro-Kubernetes, it's very easy to do a local development and deployment. It's very easy to start, and you don't need to talk to the real hardware. You can always use digital twins. So you have two fully isolated system on your laptop, and it's very portable. So it's, by the end of the day, it's just a bunch of YAML files. You can give it to other persons and say, hey, here you can install micro-Kubernetes or whatever you would like, apply those YAML files, and you will have this system running on your machine almost at no time. So obviously this opens the door to integrate with CI/CD pipelines and apply all these fancy strategies of rollout deployment, canary deployment. It might be not very important for this particular case, but on a larger scale, when we start to develop something using Kubernetes, this is super useful. And also embraces serverless design. Nowadays, scientific software faces challenges that are far beyond solutions of typical client-server architecture. You need to think more in either event-driven architectures patterns, and the systems becomes much more complex, and serverless design addresses this challenge one way or another. It's easy to share, just as I said, it's a bunch of YAML files or Helm packages. And finally, which I find the most important, it opens a window to integrate third-party open source tools. So for instance, we can integrate with observability tools and have all these very fancy GUIs and dashboards for free, and we can integrate with service meshes and then leverage the security and things like that. So next case is San Diego Supercomputer Center. This one located in San Diego. San Diego is a city in the United States, south from Los Angeles, almost on the border with Mexico. And then we have this University of California, San Diego campus with this fancy building dedicated to supercomputer center. And inside that building, we have a bunch of very nice hardware. And the unique feature of this place, yes, for me, is that some offices faces the ocean view. That's like on the picture in the right-hand side corner. And what San Diego Supercomputer does for science, so it's obviously high-performance computing, but apart from that, it's also a cloud provider for scientific projects. And I just want to step a little bit outside of the main storytelling, and just to showcase one of the, I find, very important projects that are hosted at San Diego Supercomputer Center, namely a project to analyze and prevent wildfires. So they gather a lot of data, process it, and then try to understand where the wildfires comes, and then notify the firefighters in time so that they can really do some preemptive measures. And I find this very important, and I believe everyone who is living in California for the last 5 years, one way or another, faced this issue. So for instance, I witnessed, not in California, but even in the northern part of the United States, this year I was driving from Yellowstone to Seattle, and the whole Washington state was covered with smoke. I mean, literally, you could see just a few steps away, and the smell is also not very nice. So I believe this is something very important they do. And another project, which is hosted at San Diego Supercomputer Center, and where I was involved, is this RCSB PDB website. It's basically a search engine to proteins. So RCSB stands for Research Collaboration on Structural Biology, and PDB is Protein Data Bank. So this website provides sophisticated search capabilities for biologists to find proteins. So for instance, you can search by chemical components, structure similarities, sequence alignments, and all that kind of fancy thing. And behind the scene, this is quite complex project with a lot of microservices. Here I put some print screen from internal analytics dashboard. I will dive into that a little bit later as well. But here the main message is that it's quite a loaded system. So it serves somewhat 3.5 million requests per day. They are not distributed evenly, so the peak is always working hours. It's distributed on both coasts, so on the West Coast, on the East Coast, and it's hosted by the San Diego Supercomputer Center running Ubuntu servers. So talking about my role at RCSB, I joined them in a pilot project of migrating from OpenStack to Kubernetes. So specifically, I was responsible for designing and implementing a Kubernetes platform and also lead the migration process. They wanted to migrate to Kubernetes because nowadays there is a lot of AIs thingy, there's also tons of talks, even at this event, about AIs. And apart from ChatGPT, Midjourney, and other stuff, there are AIs that predicts protein structures. And then the goal is to integrate those structures also into the website, so users can see and search not only for the experimentally discovered structures, which is, by the way, only 200K for the history of 50 years. And now it's millions and millions of predicted structures. So this is how this project looked like. I really love concept maps to do project management, and it's a complex thing, but I specifically want to highlight one technical challenge we had to address during the migration process is preserving elastic infrastructure. And namely, this domain-specific analytics. So this is again that screenshot. So on top we see like a standard metrics from a web application. So it's requests per second, how many requests, how many errors, things like that. And then we have a layer of pie charts and heat maps dedicated to this domain-specific analytics. So why this is important? Because it involves money. So this analytics is used to prepare grant proposals and do a fundraising for the next funding cycles. And also preserving the existing solution in which a lot of efforts was invested. It's like 1 year in development efforts for the search analytics engine, and it obviously costs money. So if we would fail to preserve this thing, we probably will need to start from scratch, and that will lead to direct costs of 200K roughly. And so here's a solution. It took a while to come up with it. So the main, so to say, technical difficulty was that previous infrastructure in OpenStack, every microservice was behind a dedicated load balancer. And then we took logs from that load balancer, sent it to some storage, and from there we had a bunch of scripts to ingest those, so extract the domain-specific data and inject those as the documents into the Elastic Index and provide the dashboards by the end of the day. With Kubernetes, the picture is a little bit different because now you have only one load balancer, which is ingress controller, and you can access Kubernetes only from like a single point of entry. And as the end result, what I did is basically I took the micro Kubernetes, reproduced almost a standalone sandbox of our system, and then played with different solutions and pieces. And as the end result, we have ingress controller based on HA proxy to match the previous infrastructure. And then we're using syslog to send those logs line to FluentBit. FluentBit is responsible to split the logs as it was in the previous system. And then basically everything is the same. So this solution is very efficient in terms of migration. And since micro Kubernetes and actual production Kubernetes are quite similar in our case, it was very easy to apply the solution. It's again just a bunch of YAML files we apply for production Kubernetes, deploy something, see that it works, and we are good to go. So how micro Kubernetes saved us a lot of money and efforts? Again, it was very easy to have a standalone sandbox, and using echo services to mimic the actual services, because we were interested in the log lines, not the services themselves. We could easily play with different ingress controllers and how to configure them. It also provides the possibility to use standard tools like ksniff to, let's say, listen for traffic between different ports, things like that. And it's also provided a great flexibility in connecting to a non-production Elastic cluster. So there was a very easy way to spin up Elastic cluster outside micro Kubernetes, inside, and then try different things. So the whole thing allowed very fine-grained tuning and efficient problem isolation. So meaning that when something went wrong, it was very easy to narrow down and pinpoint the exact problematic spot and just to fix it. So what's next? Kubernetes becomes de facto a standard solution for deploying applications, even in the scientific world. And as for me, micro Kubernetes provides great starting point. So it's easy to start with. It provides a lot of out-of-the-shelf solutions like Helm and different ingress controllers, observability, and all that stuff. I will invest my efforts into advocating it. So the workshops, showcases, and so on and so forth. And apparently there is a now new initiative from IBM called Open Source Science. It's relatively young, and then they specifically want to address features of scientific development, like reinventing the wheel, some gaps in skills, and so on and so forth. For me, it's the most important thing, probably reinventing the wheel. It's somewhat derived from funding sustainability, because it's always grants, so you don't know where you will have money to continue the project you are starting with, and so on and so forth. But apparently these guys are a part of NumFocus, and I saw some stickers in the hallway from NumFocus, so I would really love to talk with those guys who brought those. Yeah, and I'm a little bit faster. So if you're interested, I would really love to continue this conversation and maybe bringing together companies like Canonical and with the scientific software projects. So feel free to connect with my network on LinkedIn. And yeah, basically that's it. Thanks. Any questions?
We still have a few minutes. If anyone wants the mic for a question, just raise your hand.
Hi, great work. I wanted to ask, the deployments that you do with MicroK8s, do you have a lifecycle management tool on top? How do you do the deployments exactly?
Really in production, is it working? Okay. In production, we use micro-Kubernetes only for this first showcase. And for that, yeah, I use standard GitHub Actions to do the stuff.
GitHub Actions for the work?
GitHub Actions as scaffold. So I have a GitHub action runners with a scaffold script, and then I use the same bunch of scaffold scripts to do it locally and also to the production Raspberry Pi. I mean, it's always like next to you. It's not elsewhere.
Cool.
With the San Diego Supercomputer Center, it was just setting up a micro Kubernetes. I mean, there was no point to have really pipelines to do stuff. It was mainly for experimenting. So it was like disposable entity, which, okay, I screw everything, I just throw it away and start from scratch with another instance.
Cool, thanks.
Sure.
Anyone else?
Is it possible to say node numbers, something like that? You know, how many nodes?
Yeah, for the first showcase, it's just one node, that specific Raspberry Pi. For San Diego, I played with multiples, but Docker-based, I think.
How about the rough numbers, like 10, 12, 100?
Just 2, 3. Again, this was more on experimenting and research and development side. In production, we have 5 bare metal nodes each coast. So these are really huge machines on each coast, 5 of them. So 10 in total.
Do you have separations with controller nodes and worker nodes? Or, for example, 5? How do you divide 5 nodes?
There is one typical control plane node, and then I think that like 2. I think it's 2 worker nodes, and then 3 nodes dedicated to storage. So it's runs Ceph and that kind of things.
Thank you.
Sure.
Thank you, Igor.